the next one here. Next one is number 9. Good question here. Let me share my screen here. Get started here in round 2 today. All that's connecting here. Let me find number 9. All right. So number 9 says this. Active figure 34.4b shows a plane electromagnetic sinusoidal wave propagating in the X direction. All right, well, let me pause there and just grab the book here because it would be good to see that picture. They don't give the picture in the question, but they say 34.4. And so here it is, 34.4, and then B. And so they say here is the electromagnetic wave. And again, the electric field, they're trying to show you sinusoidal. They're trying to show you that it would be in the Y direction. Remember, the energy flows in the X direction. The B field would be this green one. It's in the Z direction. So notice that the E and the B field are not only perpendicular to each other, but they are perpendicular to the direction of travel. And so it travels along the X-axis, yet the electric field is along the Y-axis, and the electric field is along the Z-axis. All right, so keep that picture in mind, because I'm sure this is part of it. So it says, active figure 34.4b shows a plane electromagnetic sinusoidal wave propagating in the X direction. Suppose that the wavelength is 50 meters and the electric field vibrates in the XY plane with an amplitude of 22.0 volts per meter. Calculate A, the frequency of the wave. All right, so the velocity equals wavelength times frequency. Since these are electromagnetic waves, they travel at the speed of light. And so the frequency would be C divided by the wavelength. So the speed of light is about 3 times 10 to the 8th. The wavelength here is 50 meters. And so quick calculation, 3 times 10 to the 8th divided by 50 is 6.0 times 10 to the 1, 2, 3, 4, 5, 6. So 6 megahertz would be the frequency. All right, B. B says the magnitude and the direction of the magnetic field when the electric field has a maximum value in the negative y-axis. All right. The ratio between the electric field and the magnetic field is equal to C. It doesn't matter what point in space or time. This is the connection that was worked out in some section. Let's see the section, he gets it. Yeah, somewhere in this section 3, the same as the picture. He's got a lot of equations. I don't see it explicitly. Oh, yeah, I do. I guess it's 34.21. He says that pick any moment in time and any place in space. And if you put a dot right there, if the electric field is changing and the magnetic field is changing, in other words, they're creating each other, they have to be related by this factor of C, the speed of light. So that is whether we're dealing with minimums or maximums at any moment in time also. So any place in space, any place in time. But he goes on to say that we are to find the magnitude and the direction of the magnetic field when the electric field is at its maximum. All right, so the rearrangement of this would say maximum electric field divided by C would be the maximum magnetic. So they say that the electric field, a maximum of 22. So 22 volts per meter is the maximum electric field. And so if we divide that by the speed of light, we get a 7.33 times 10 to the minus 8 Tesla. So this would be the maximum magnetic field. And actually, maybe I should have used the word minimum, because he's very clear to say when the electric field is at its maximum value, but in the negative direction. So coming back to this picture, the electric field would be at its maximum negative here, making the magnetic field its maximum, but in the negative Z direction. So this would be a, put it like a field, so negative K hat direction. So again, the magnetic field has to be perpendicular to the electric field, and it also has to be perpendicular to the direction of travel. So it's got to be perpendicular to both X and Y. All right. C. I'll write an expression for the B field with the correct unit vectors, with numerical values for maximum K, which is the angular wave number, omega, which is the angular frequency, with an amplitude of this form. So in other words, B vector would be B maximum cosine of Kx minus omega t. All right, so I'm going to kind of assume here, see what the answer says. But I think they're trying to make it look like this picture where it starts at like a cosine for the electric field. So it also starts with a cosine for the magnetic field. So it starts at its maximum in the positive Z direction. Okay, so I can write this then as B equals. And so ignoring the negative, I can put its maximum value with a K hat direction. So there's its maximum magnetic field. And then the angular wave number is 2 pi over the wavelength. So this would be 2 pi over, and I believe it was 50. Yeah, 50. And then this would be the X. And then it would be O minus, and then again, this would be 2 pi omega, I'm sorry, 2 pi F for the angular frequency. So we've got a 6 here. So if you go times 2 pi, maybe I'll write that then as 12 pi, because 2 pi times a 6 makes 12 pi times 10 to the 6 t. This would be a mathematical way of writing out the equation for the magnetic field. That's page 1. Looks like this only needs a page 1. There is no part C. Although, let's just scan solutions. Let's see. They do 6 megahertz. Good. They do a negative K hat direction. Good. And they do 73 times 10 to the 9. Okay, so same number there. Now here, now this is interesting. They did put a negative here. They've got that number. they actually worked this out. So 2 times pi divided by 50.216. Okay, so we agree, 216 x minus, they got a minus. Oh, and they multiplied this out, 12 times pi. Well, that should have been a plus 6. I don't know what I was thinking there. Times a million. And 3.77 times 10 to the 7. Okay, so we agree there. I still question that negative. Let me go back and read the question a little bit. Write an expression for B with the correct unit vector with numerical values when its magnitude has this form. I'm not sure that question is saying it should start with a negative cosine or a positive cosine. So I think the plus or the minus way it's written is acceptable. Anyway, so I took it to interpret the positive. They got the negative, but good thing is we're saying the same thing. So I'll call that good. All right. So cross out number 9 and let's look at the next one. It looks like you guys are asking for number 11. Huh? Okay. Number 11. 1244. All right. So number 11 says the following. Number 11 says in SI units, the electric field of an electromagnetic wave is given by this equation. So maybe I better write that down. So the electric field in the y direction is 100, and it's a sine. And it looks like it's 1 times 10 to the 7th x minus omega t. Okay. Find A, the amplitude of the corresponding magnetic field. Well, again, as I just said in the last problem, the ratio of the electric field and the magnetic field. So they, at a given point, pick any point in space right here, if they are creating each other, they will be perpendicular to each other, and the ratio of their strength is given by C. Hang on just a second. Needed to look out the window and see what was going on. Sounded like a lot of activity. All right. So in this case, the magnetic field would be the electric field divided by C. So the electric field is 100, and C is 3 times 10 to the 8th. I guess that makes 1/3, which is 0.333, times 10 to the, you subtract this, you get minus 6. So that would be 3.33 times 10 to the minus 5 Tesla for the magnitude of the magnetic field. So find the amplitude of the corresponding magnetic field oscillation. B, the wavelength. Well, this number out in front, which is 1 times 10 to the 7th, is 2 pi over its wavelength. So that's what we call its angular wave number. So that would be a 2 times a pi, and we would divide it by 1 times 10 to the 7th, coming up with 6.28 times 10 to the negative 7 meters. So about 628 nanometers, which I guess would make it kind of on the red-orange barrier, maybe more red than orange. Be visible, though, in the electromagnetic spectrum. It would actually be very, very close to that red beam you see maybe on a scanner. at the grocery store, some checkout line, those self checkouts. They scan it with that optical scanner, and they use that Heaney laser, which is 6.328. All right, so there is B, what's the wavelength? And then C, what is the frequency? Well, the frequency, again, would be the speed divided by the wavelength. So the speed is 3 times 10 to the 8th. And if I then divide it by that last answer, which is the wavelength, we're looking at 4.77 times 10 to the 14 hertz, about 477 terahertz. Hang on again. All right. Yeah, dog's barking there. I can get more activity. I got a delivery of some type at my door. Get that later. Okay, so there is the frequency. What else did they ask? Oh, and that's it. Oh, good. So not a real long one here. Only one page. Let me check the solutions. Make sure I'm kind of going along here. They got okay, same number there, same number there, and same number there. Nice. Okay. Very nice. All right. Cross that out. Well, let's try another one. About, again, chapter 34, number 16. That'll be a good one. And the next one on your guys' list here. And what is it? 1249. All right, let's see what number 16 says. 16 says that you have an AM radio station. It broadcasts isentropically, and that means uniform in all directions, with an average power of 4 kilowatts. A dipole receiving antenna of 65 centimeters long is located 4 miles from the transmitter. Compute the amplitude. Hang on, this again. Okay, hey, step right. All right. Calm my dog down a little bit. The package, maybe. Yeah, let's leave it there for a while. Okay. So where was I? Oh, yeah, this AM broadcast. So number 16. So 4 miles from the transmitter. Compute the amplitude of the EMF induced by this signal. Now, this might actually take a little bit of discussion of the physics behind it before we know how to apply the math, because it's putting together quite a few things. The big part is this chapter, but also some previous chapters. So let's just say I have this transmitter up here. I won't try to draw it any fancy way, but here's my transmitting tower, and it sends out these electromagnetic waves. And they make it very, very clear that they go equally in all directions. So that's extremely helpful, because if you're way over here 4 miles away, that energy would now be spread out on the surface of a sphere. And you can see that as it goes further and further and further out, the surface area of this sphere keeps getting bigger and bigger and bigger. And we know the intensity is the amount of power over the area. And so what happens as you get further away from the transmitting tower, the same power gets spread out over a bigger area. So your intensity goes down. And your intensity is related to the energy density. Energy density times the speed of light is that in intensity. And maybe I'll just point out here, your author works this out for you. Aha. Like equation 26, right? That the average Poynting vector, or the intensity, is the speed of light times the average energy density. So I'm going to take advantage of that because the energy density is related to the electric and magnetic field. Half of the energy is in the electric field and half of it is in the magnetic field. And what I'm saying here is that somewhere over here you have an antenna, and the antenna, if it's a straight antenna, and I think they implied that, did they not? What did they say? A dipole receiving antenna. So what they mean is just a straight wire sticking up. And it will then have electrons forced up and down because of the electric field. And so what I would like to know is how strong is the electric field over here where the antenna is? The antenna is 4 miles away. And obviously, that electric field, which is in the energy density, is connected to the intensity. So let me start there. That'll be kind of the first step. And so the power is the 4,000 watts. Now that is spread out over the surface area of a sphere, which is 4 pi r squared, which then gives me the energy density times the speed of light. Now, the r is going to take a little bit of thought because they give me the 4 miles. And that's not the SI units. We need to look up that there is 1,609 meters in 1 mile. So if we take the 4 times the 1,609, we are talking about 6,436 meters away. All right, so if we take I'll do the area here. So if we take this distance and square it, multiply by 4 and multiply by pi, that's the area. And so 4,000 divided by that, that's not what I wanted. 4,000 divided by the last answer will give me the intensity. So the intensity at 4 miles away is 7.68 times 10 to the minus 6 watts per square meter. If I then divide that by the speed of light, we're looking at an energy density of 2.56 times 10 to the minus 14 joules per cubic meter. Now, granted, not much energy, but I guess you wouldn't expect that. Nobody would sit 4 miles away from a transmitting antenna and feel like they're getting, warmed up from the energy coming from the transmission tower. This would not be the same as sitting in the sunlight and feeling warmed up, or sitting in a microwave and getting extremely warmed up. So this is our energy density. Let's call this page 1. Okay, so page 2 then would say, okay, how does this relate to the electric field? Well, the energy density, as your author writes, is made up of 2 pieces. One is the electric field, and the other is the magnetic field. There's different ways your author can write this. I'm going to write it this way. Because what's the question? question says, compute the amplitude of the EMF. So they want the amplitude of the EMF induced. So to get the maximum EMF, I really need the maximum electric field. I guess this is best done by pointing out that your author got this by saying, if you looked at the average energy, so R and S, of the electric field and the average RMS of the magnetic field, and you add the two together using the fact that the magnetic field and the electric field, the ratio between electric and magnetic field is the speed of light, you can combine these two and get mu naught times the RMS of the electric field squared. That's basically saying this term and this term have the same value. And sure enough, they do. So there is equal amounts of energy in an electromagnetic wave. There's an equal amount that is electrical and an equal amount that is magnetic. And so if we add those two together, we get rid of the 1/2. So it'd be like 1/2 plus 1/2, and we get a whole. Now, if you write that in terms of the maximum, remember that if you take the maximum and divide it by the square root of 2, you get the RMS, and then that leads to this. So that was kind of quick, and I didn't go through every step, and nor did I really want to go through even maybe that many steps. Just wanted to point out here that this first step, getting the energy density, was the first goal. Now I'm going to use that to get what is the strength of the electric field. And so let me put in my numbers here. This is that 2.56 times 10 to the minus 14. This is 8.85 times 10 to the minus 12. And so this will give me the strength of the electric field. So the energy density is still in my calculator. So let me move the 2, multiply by 2. Let me divide that by 8.85 times 10 to the negative 12. And now let me take the square root. And so we're looking at an electric field of 0.0, I'll call it 761 volts per meter. Now, the last step is to say, well, if this is the electric field, remember that the voltage is this integral of E dot ds. And so the voltage is the summation of the electric field. This is our chapter 25. What is the voltage? Now, if you have a constant electric field and the electric field is in the same direction as your wire, so assuming the electric field is vertical and the antenna is vertical, this would just become E times D. So it would become the simplest case. And so we've done a number of those, especially like in the capacitor, where the electric field and our direction of integration were the same. We just had E times D gives us the voltage. And so I'm going to take advantage of that to say, okay, again, the voltage, of course, they call it an EMF, okay, since it's induced here, would be that electric field, and maybe I should say the maximum voltage, would be the maximum electric field, because the electric field is changing with time. But at some moment in time, it does have this maximum, and then times the distance. Let's see, how long was this antenna? Number was it 16? Says induced the signal between the ends, dipole. 65 centimeters. So it would be this value, 0.0761 volts per meter, multiplied by 0.65 of a meter. Okay, so times 0.65. And it looks like I'm looking at about 0.0, I'll call it a 49 volts. And so about 1/20th of a volt. So not much, but certainly plenty enough to pick up, like 4 miles away. And even a simple antenna would work with that really well. And so that antenna then picks up the changing electric field, which then goes into whatever device it is. Let's say this antenna is for, well, they said a radio, so I guess be a radio antenna, but maybe by today's standards, it might be better. It's a Wi-Fi, and so I've got my laptop and I pick up this much voltage in the antenna that it's kind of strung around the screen of my antenna. And that, so really, it sounds very little voltage, but for picking something up and then amplifying it inside of my computer or my radio, that would be really, really simple. Not a problem there. And I'll just check the answer. They got, 49 milli. All right, good. Now that was a little deeper one, a little more challenging. All right, what's next here on the list? Looks like number 20. So,
hey, Professor Young.
Hey, yeah, fire away.
Hey, just was wondering, have you done number 3 yet by chance on chapter 34?
Oh, I did. When did I do number 3? Oh, I did it in the first session. I did number 12, 3, and 4. And I thought I saw you in the first session, but maybe I didn't see you till number 4.
Yeah, I think I jumped in like in the middle of 4, so I wasn't really following.
Okay.
Well, if you upload the videos to
I will.
YouTube or if you have, when do you think those would come out for the videos?
Oh, tonight. I usually let's see. I guess we usually do this till about 5, and then I get something to eat, take a break, and then I let the computer process all the video and upload it, and then send out the list. Yeah, I guess what I'm getting at is I could redo number 3 with you or for you, or we could, it looks like it took about a half hour to go through. 26 minutes. Or should I just send you the video?
Yeah, I might wait for the video, or if you have the paper still on hand for how you personally went through it, that would also be great.
Oh, yeah. You know what? Oh, yeah. Now there is a lot of detail here about symmetry. Oh, yeah. Let me encourage you to see the video on this.
Yeah. Okay.
Yeah, because I'll do it again for you if you want. I think we'd be better off to go through these other lists though, and then circle back to you.
Yeah. I know. If you did it already, that's what I was thinking. Like, oh, maybe I'll just wait off for that one.
Yeah, but I'll show you here that this number 3, because number 3 has the new term for Ampere's law, and then you have the integrals to do and the flux. So there's 2 integrals, and then there's directions, and all of those are, yeah, it's kind of nice. I see why it's almost a half hour long. It's nice to kind of explain why this angle is 0, why I pull the magnetic field out. Same thing over on the other side, why that term is 0. Yeah. So I don't want to leave you hanging too much, but I think that would be best if I did the other ones on the list. 1, 2, 3. I got like 7 other ones that I haven't done yet that people have asked.
Yeah, I got you. I could probably just skip over it for now, and I can try following you from, what is it, like 16 and on? You finished 16 just now, like number 20.
Yeah, I think that's good advice. Yeah, let's go to number 20. That's next on the question list. Okay, so I'll say let's try number 20 here at 107. And I better put a page 1. Some of these can get long, although a few of them recently have been kind of short, but that last one was at least 2 pages. And actually, maybe I don't want to speak too quickly, but I think the problems in this chapter, the problems aren't so long. That's not to say they're easy. So that's to just say maybe I don't need quite as many paper and maybe won't take quite as long, but knowing what's going on, especially that last one I just did, number 16, is a little challenging. All right, well, let's just see what number 20. Oh, good. 20, actually 20 is just like 16. So it's worth seeing this one a second time. Because 20 says, assume that the antenna of a 10 kilowatt radio station radiates electromagnetic waves, compute the maximum value of the magnetic field when you are 5 kilometers from the antenna. And then state how this value compares to the surface value of the Earth's magnetic field. Okay, so same idea, and I'll kind of maybe draw the same picture that I got started with the last one. If I have this radio transmitter and it transmits these electromagnetic waves, these radio waves, in all directions, and I get at some point over here, point P, that energy, which in this problem is a little stronger. The last one was only 4 kilowatts. This is a 10 kilowatt radio station. But the energy gets transmitted over a sphere. Try to draw this like a sphere. And so all that energy is spread out over the area of a sphere. And so the intensity is defined as the power in the waves or the fields divided by the area that it's spread out. And so as you get further from the transmitting tower, the area gets bigger. So the total energy flowing out doesn't change, but it's spread out over a bigger area. So the intensity goes down. So in this case, we would have the 10 kilowatts. So let me write it as 10,000 watts. And the surface area of a sphere is 4 pi r squared. Now, let me come back to the problem. We were how far away? 5 kilometers. So that is 5,000 meters. So that gives me an intensity of 10,000 divided by 4 divided by pi divided by 5,000 squared. And so we're looking at 3.18 times 10 to the minus 5 watts per square meter. And so that's kind of the first step we did in the last problem, and the first step also in this problem is to find out what the intensity is. Now, the reason that's relevant is they say compute the maximum value of the magnetic field. Okay, so the intensity is equal to the energy density times the speed of light. And the energy density, as we were just talking about, is 1/2 epsilon naught and the maximum of the electric field squared. And now I guess I have a decision to make. Because in the last problem, I wanted to know the electric field. So I did this calculation. And so maybe I'll do that again, but I could go and remind myself that it's an equal amount of energy in the magnetic field and the electric. So instead of having a 1/2 epsilon naught E squared, I could have a B squared over 2 mu naught for the energy density and get directly there. But for whatever reason, partly to match the last one, and partly to then remind you that once you have the electric field, you also have the magnetic field. If you're dealing with electromagnetic waves, if the two fields are created from each other only. So this doesn't work way back early in the semester when we had like electric fields just by themselves. We didn't have any magnetic field, so this ratio made no sense. But this is when the electric field is producing the magnetic field and the magnetic field is producing the electric field. So if that's all you have, in other words, if you don't have charges, moving charges also made a magnetic field, and charges themselves also made an electric field. So if you don't have any charges, so we often call this free space, then that ratio, once you know one, you also know the other. That's the other way of the fields make themselves. So I think I'll follow this path here. And so I'll start with getting the electric field, because the number in my calculator is already the intensity. So if I multiply it by 2, divide it by 8.85 times 10 to the negative 12, and then take the square root of that, I get a field that is about 2,682 volts per meter. Now you can kind of see if I take that field and divide it by the speed of light, I would get the magnetic field. So I'll take that and divide it by 3 times 10 to the 8th, and I'll get the magnetic field. So 8.95 times 10 to the minus 6 Tesla. And presumably, if I'd gone this path, it'd been one step, and maybe that was a better way, but wanted to kind of just reminded you of this and follow the same one as we did last time. Now, I think they said up here to compare it to what the Earth got. But I thought I would check my answer just to make sure. Oh, yeah, and we got a very different answer. Oh, I forgot to divide by C back here, didn't I? I was focused on that and forgot that one. All right. My bad. Let's try this again. All right. Okay, so intensity. So 3.18 times 10 to the negative 5. So that's the intensity. Then I multiplied by 2. Then I divided by 8.85 times 10 to the negative 12. And what I didn't do, should have done, I'm going to do it now, is also divide by the speed of light. Yeah, I should have known. That would be a huge field. Okay, now, don't forget to take the square roots. All right. So this was 0.155. Now, if you take that and looking at this equation and divide that by the speed of light, also 3 10 to the 8th, you get a number that is 5.16 times 10 to the minus 10 Teslas. All right, and I think that's what I saw when I looked over here, the answers. Yeah, well, 10 to the minus 10. Okay. Now, the last part of this then says, compare this to the Earth's field. Now, when we were introduced to the Earth's field way back in chapter 29, we said it was about a half a Gauss, which would be 5 times 10 to the minus 5 Teslas. So they each start with a 5, but this has -10 and this has -5. So there's 5 zeros between them. It's 100,000. So the field from the Earth is 100,000 times more than the field from these radio waves. So much easier to detect the strength of the Earth's magnetic field than it is to detect these radio waves. However, I should be careful. This, even though this sounds so incredibly small, that's not with today's technology. That's very reasonable. You could easily have an antenna. I mean, you can easily pick this up. So that's, well, you can see it better with the electric field. You know, that's a tenth, almost to 2/10 of a volt, and that's easy. I mean, we can easily pick up things that are in the microvolts. Some of our telescopes, like Goldstone out in the desert, to pick up the transmission from Voyager way out there, you know, something less than nanovolts that thing picks up. An incredible antenna. So normal antennas couldn't get that small, but easily this is huge. So anyways, it's 100,000 times smaller than the Earth. So that makes it sound small, but I don't want to leave you guys with the impression that that's some kind of small value. You know, very understandable, very reasonable to work with in terms of an antenna. All right, let's see. Next on the list, number 25. Okay, and the time is 1:18. All right, so chapter 34, number 8. Oh, what I said, no, number 25. When I get 18, oh, that was the time, 1:18. Okay, so let's try this one next. Okay, so number 25 says that, oh, high-powered lasers in factories are used to cut through cloths and metals. Oh, this is fascinating. Boy, I saw this the first time I saw this. I was just in awe. They had this stack of plywood. I mean, it was plywood upon plywood upon plywood, and I'm not sure how many stacks of plywood they had. But this laser came down and just cut, vaporized all the way through, and cut something like a stack of 10 sheets of plywood in one shot. And plywood looked like this, and the laser just went. And then had this piece, and had 10 of those pieces, and whatever parts they were making. I think if I remember, it was like one of these self-assembly boats. And so it had all the parts, and they just manufactured them and sent out the parts, and you got it to your house on probably an Amazon package. And then you put together your little rowboat here. And it was, just very impressive. And seen them cut airplane parts. Just, yeah, amazing when they went from mill heads to lasers. It's probably the 90s. But anyways, high-powered lasers in factories are used to cut through cloth and metal. And they say figure 25. All right, I'm going to jump over to figure 25. I'm not sure what they're referring to. I don't remember seeing a figure 3425. Oh, they do have a little photograph here. All right, here's a little photograph in a factory, and looks like there's cutting through the metal piece. Oh, nice. And of course, you can see everything vaporizing. It looks more like sparks, and kind of makes you think like you're cutting it with a torch or something. But and I guess it's the same end effect as a high-powered torch, but it's blasting through with a light beam. All right, so high-powered lasers in factories are used to cut through cloth and metal. One such laser has a beam diameter of 1 millimeter and generates an electric field having an amplitude of 0.7 million volts per meter at the target. Find A, the amplitude of the magnetic field. Okay, so let me say it again. If you take the electric field and you divide it by the magnetic field, you get the speed of light. Now, I should be careful. That is only when the electric and magnetic fields are created from each other, not from your charges. So, don't confuse that back with, when we did electric fields due to charges back with Gauss's law and Coulomb's law. That wouldn't apply. But when the electric field is changing and makes the magnetic field, and the magnetic field is changing, which makes the electric field, there is a connection between them. And that was the whole point of this section of the book, to say that when they create each other, you don't need any charges around there, hence electromagnetic waves. There's no charges between, say, the sun and the earth, yet still those electromagnetic waves propagate all the way from the sun to the earth. They don't need any charges. They make each other. Anyways, that ratio is always the speed of light. So B would be E divided by C. So A is just simply taking what they gave us, the 0.7 million, so 0.7 million, and divide it by the speed of light, and we would get a value of 0.002 Tesla, which you could expect that both this electric and magnetic field, these are strong fields. That makes sense. Make it real hard. They're going to cut through metal. So find A, the amplitude of the magnetic field. B, the intensity of the laser. Okay, so like the other problems, the intensity is the energy density times the speed of light. And the energy density, we can either get that from the electric or the magnetic field maximum. But I'll take the electric field and putting in my calculator here, 0.5 times 8.85 times 10 to the negative 12, excuse me, times an electric field, which is 0.7 million squared, times speed of light. And so 6.50 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 watts per square meter. Again, amazingly big number. But of course, that's the energy in 1 square meter. And so this laser beam is focused way, 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 way small. So that makes the intensity seem extremely high, even though the energy may not be all that high. But probably a pretty good energy. Let's see, the intensity. Yeah, then there is C, good. The power delivered. So since intensity is power over area, the power would be intensity times the area. So if we take the intensity, 6.50 times 10 to the 8th watts per square meter, and thinking this laser beam is this little spot here, the energy would be spread out in an area, so it'd be pi r squared, pi. We have it in a circle. And I think they said the diameter, not the radius, was 1 millimeter, 25. Diameter, yeah. So the radius is 0.0005 squared. And so taking this intensity, multiplying it by pi, multiplying it by 0.0005 squared, you get an energy of about 510 watts, meters squared. So 510 watts is quite a bit of energy, but a typical light bulb, what, a 100-watt light bulb. But if you had like a chandelier that's got 5 of them above your dining room table, that's 500 watts. That's, not that much energy in of itself. But the real key is it's that much energy in this small area, making this huge intensity, which makes a huge electric field. In fact, the electric field is so high that it rips the electrons right off of the atom, just vaporizes anything it touches: cloth, metal, carbon fiber. And so that's how they were making the airplane parts I was talking about. Nice carbon fiber, fiberglass. I mean, you name it, it just cuts right through it. So that's the idea of number 25. Let me just kind of check my numbers with the solutions, see if I made any little mistake. 2 milliteslas. Okay, good. They give 650 mega. Okay, good. And 510. Okay, good.
Professor Young?
Yeah.
So this was just out of curiosity, but I used to own a laser, and I would like shop around and see like that they would sell it with like a description of how many milliwatts it was. Like the weak ones were like 5 milliwatts, and would a better measure of it be that intensity that you're talking about, so that it could cut through, like you said, those materials and stuff like that, or is the power still?
Yeah, no, I think the power is best. Like if you get a little laser pointer, they usually say something like less than 5 milliwatts. And the reason the intensity is not as useful or as important, because you can control that by sending the laser through optics. And that's really kind of the danger in these handheld lasers. In fact, anything above 5 milliwatts is considered dangerous, because if you shine it in your eye, your lens in your eye will focus it to a really small area, whether you intended to or not. And the intensity can go really high, and it can really just rip apart the structure of your eye, the retina and stuff. So this laser obviously has a lot of energy, and when you focus it down, it just vaporizes anything. And so obviously if it hit your eye, but this one is so high powered, if it hit your skin, it would rip apart the atoms that hold together your skin and all the DNA and all the things in the cell wall. And so it would just cut right through it. But 5 milliwatts, you put it on your skin, it's spread out over enough area that it doesn't destroy the cells. It's not till it accidentally or purposely goes into somebody's eye that it angles down and becomes really dangerous. So that's why almost any laser is just very dangerous when it comes to working with people's eyes. Now, this is their cutoff of 5 milliwatts. So 5 milliwatts is supposed to be about the value that if you were to shine it in somebody's eye and it focuses down, there is such a bright intensity to their retina that they will flinch. They will move their head, they will blink their eye. And so it doesn't last very long, and it doesn't do any permanent damage. So most of these laser pointers, when you get into your eye, you see spots for a while. You might even have spots for a whole day, but it doesn't seem to do permanent damage. It's when you get above this 5 milliwatts. So anyway, that was a long way around your question. Your question was, should they list it by intensity? And I would say no, because the intensity is a function then of what happens to the light after it leaves the laser. In fact, even a laser pointer, you can see it really well. They all spread out. Like, this is kind of my laser pointer. It is spreading out. And so if you've ever done a laser pointer and you're close, like you're giving a lecture, when I give a lecture and use the laser pointer, kind of close, and it has a small dot. But if I shine it on the back wall or across the room on the periodic table, it's a big dot. And so it is spreading out. So again, to say what the intensity is doesn't really help, because what the intensity is, it would depend on how big the beam is, and how big the beam is depending on where I shine it, how far away. So again, labeling the intensity of them is not the key, because the intensity can be either increased or decreased depending on what happened after it left the laser beam. That helps.
Got it. Thank you.
Yeah. Okay, good. And thanks for the question. All right, let me cross out number 25 and go to the next one on your guys' list. Looks like it's 28. And I'll start this at 133 here. So chapter 34, number 28. All right. See what 28 has to say. Oh, yeah. And this is the first time I've got a question on either momentum or pressure. So I should probably spend a little time on this, because I think that this is a little hard to digest. And I know your author did a good job in section 5 and explain it. In fact, I'll make a little disclaimer here. I said it in Sunday night when I put out the information about the test, that I won't test you on section 5. Kind of neat to see. I'm glad I assigned some homework for it, but 5 and 6, and I didn't assign anything from 6. Not really much that can be, but section 5 also. I gave a couple of homework problems, but also said, I just felt it would be a little too much at the very end, and left it at that. Okay. So know that from the beginning. And it looks like these are the next 3 on your list here, the 28, 31, and 32. So nonetheless, I'll do them. But like I said, take this for your learning. It won't be on the exam. And so it's important, because as far as your learning, you'll see it more later on. So again, I wanted to touch it on a little bit. But here's what I'm getting at. Way back in Physics 121, when you did mechanics, you defined momentum as mv. That was nice, because when you took the derivative of the momentum with respect to time, you said the mass was a constant, and then you took the derivative of the velocity and you had ma. And so you had what we called Newton's second law, that says force is mass times acceleration. But these equations are not complete. They're really good when you're working with stuff that has mass, but electromagnetic fields do not. And so again, this can get misleading, especially when we deal with light, because a beginning student will look at this and says, well, light has no mass, so this number comes out to be 0. Even if the speed is really high, it comes out to be 0. And sadly, that's not quite right. That's not quite the whole story. It would be also like saying, well, you can't have any force, or you can't have any pressure unless you have mass. And that's not true either. That one I think you might understand a little better. You might say, well, electric fields put a force. Now, if they push something with mass, we can say the force they push was equal to the mass times the acceleration of that object. But what if it's something without mass? Does it apply a force? And so, yes. And so a laser beam, a light wave's coming from the sun. And I think that's what this one is about. They do have momentum, and they do apply a force. And I think maybe the better way to see this is to take what you do know from physics 121 and say, well, you started 121 with the idea of force, but along the way, you equated force to, excuse me, two different things. One of them was how the energy changed with space. Another one was how the momentum changed with time. So if I were to just kind of bypass your beginning thoughts, you would say then how energy changes with space is how momentum changes with time. And now you might feel more comfortable with this. You would agree that light has energy. You probably would agree that that energy is spread out over space. You probably would also agree that things change with time. So what changes with time? Must be the momentum. So this is my weird way of trying to say that you can have and show that light waves or radio waves, any electromagnetic waves, does have energy and it has momentum. And because it has those and they change, it has a force. And a force over an area means it has a pressure. And so just like putting your hand up and letting it get hit with, say, a baseball, you would feel that force, that impact. You put your hand up and shoot it with a laser beam, there would be a force. Now, as you're going to see, the force is so incredibly small that you would never be able to detect it. And again, that's probably why it's hard to convince students that there is a force of impact when you get hit with light. Everybody knows if you, say, walked outside of your house and somebody threw a baseball at you, you would get impacted and you'd go, oh yeah, I was hit by something. But nobody goes out the front door and he gets to the sunlight and goes, wow, I was hit with sunlight. You often feel it's warmth, so it's got a lot of energy, but it has very little momentum. So does it have momentum? Does it impact a force? Yes. A lot? No, very little, which again is what I'm trying to indicate. There is some there, hard to convince you because you haven't ever felt it. And you can kind of see it in this derivation, if you will. And I think what we are going to need is momentum and pressure. So let me do both. Maybe the thing to do is to move the dt over to here. And so I've got a dt, a du, a dx, and a dp. If I group the dx and the dt together, so let me put the dt down there, this would be dx dt. This would be saying, how does the radio wave or the light wave change with position? Well, that's the speed right there. So du over the speed of light is dp. And then if you integrate, you're going to say that P for momentum would be the energy over C. So these electromagnetic waves have momentum. That's what this P is, which, by the way, I'm about to do pressure. So I'll try to make a capital P, but try not to confuse this lowercase p. This is the lowercase p. This is the momentum. And so momentum would be the energy divided by C. Now, C is a huge number. So you can imagine, as we were talking about a laser beam a moment ago, that if it's like 5 milliwatts, you take 5 milliwatts, divide it by a huge number, and that's a really small amount. So that's why, you know, taking your hand and shining the laser beam into your hand and having it impact with a certain amount of momentum, the amount of momentum per time is really, really small. And again, that's why you would say, well, it's just light. It doesn't have any momentum. Some would say, well, it doesn't have any momentum because it has no mass. And that's not true. And so I'm trying to say it does have momentum. It does make an impact. It does make a force. It's just so incredibly small that you're going to say, it's zero. But it's not zero. It's just small. Negligible, and you don't need to think about it, especially in engineering. Yeah, true. Unless you're talking about something big, and unless you're talking about something you could use. Now, hang on for a moment. Let me go a step further here. Let me kind of undo this equation and keep going. If I took the time derivative of both sides, this side would be energy per time. This would be power. Now, let me spell it out so I don't use a capital P. So power divided by C would really be how the momentum changes with time. That would be force. And then if you divide both sides by area, power over area is intensity. So intensity divided by the speed of light would be force per area. That would be pressure. And maybe I should write this out. This is momentum. So that was kind of my lecture. Actually, I need to kind of go back. I know I said I wouldn't put it on the test. I might not even have lectured on it. This might just be the only lecture you're getting on here. But this is the equation I'm going to use. I'm going to take the intensity divided by the speed of light and say that is the pressure. Okay. Now, let me read the question. Now that we kind of got the physics out of the way, I'll even call this kind of a page 1. We're really not even beginning till we get here to page 2. But here on page 2, it says, a possible means of space flight is to place a perfectly reflecting aluminum sheet into orbit around the Earth and then use the light from the sun to push this, and then they put in quotes, solar sail. So, and that's what I'm really getting at. There would be a pressure. And so if the light came in and just got absorbed, just hit it, boom, it would be like a baseball hitting it and getting caught, it would make an impact and push the sail. So if I let this kind of be this big sail over here, maybe I'll put the sun. The light's going to hit it and cause a pressure. And that's what I'm getting at here. Now, I'll even do you one better, because the way I worked it out, the way I described it as this is the momentum being caught. But if it ricochets off, and so just like we did in Physics 121, it takes more force to have a baseball hit and bounce off. That's a bigger change in momentum because you go from positive bouncing off and going to negative. That's a bigger change in momentum than just being caught. And I calculated what would happen and the pressure would be if you just caught it. If you reflected it, the change would be twice as much and the pressure would be twice as much, which is what you would want to do if you were trying to push something. You'd want it to bounce off because you get twice as much impact force. And so I'm going to say here for our problem, the pressure is going to be twice the intensity divided by the speed of light. Remember, I derived intensity divided by the speed of light, but I'm going to double it because the light's going to come in and not just get absorbed, but bounce off. And so there's got to be a change in momentum as it's being caught and an equal amount of change in momentum as it's being pushed back. Again, just like a baseball. Now, we're trying to then push this. And so maybe what you actually have is a small satellite here. But these rods sticking out, making a huge aluminum sheet that reflects the sunlight. And so it is this, what we call the solar pressure. We're using it as what you might call a solar wind. And we're pushing it with the light carrying momentum. All right, so let's come back to this problem. A possible means of spaceflight is to place a perfect reflecting, so here it is perfectly reflecting aluminized sheet into orbit around the Earth, and then use the light from the sun to push this solar cell. Suppose that the cell has an area of 6 times 10 to the 5 square meters and a mass of 6,000 kilograms and is placed in orbit facing the sun. A, what force is exerted on the cell? So remembering that pressure is force over area, I can then say that the amount of force would be the pressure times the area. And as we just said, the pressure is twice the intensity divided by the speed of light, and then we can multiply by the area. So this is 2, and the intensity out in outer space, they go on a little bit later to say that the intensity is 1,370 watts per square meter. And that's about the intensity when it reaches our Earth. It's about 1,000 by the time it gets down to the surface. So when you're dealing with solar cells, we often say the intensity is 1,000 watts per square meter, because that's what makes it down to the surface of the Earth after going through the atmosphere. But the top of the atmosphere, so the distance from the sun that we are at, gives us about a 1,370 watts. Remember, I'm dividing it by the speed of light. That's why I said this pressure is really small number. You would never put your hand out into the sunlight and go, oh, wow, it's pushing my hand back. I can't hold it. Never going to be enough for that. But when you multiply it by a large area, so 6 times 10 to the 5, so very, very large cell, you can get a reasonable amount of force here. And so this is not an unreasonable process. This is, science fact, not science fiction. You can actually push things with the sunlight coming from the sun. Let's see how much force that is. So this would be 2 times 1,370 divided by the speed of light, then multiplied by 6 times 10 to the 5. And we're looking at a force of a simple 5.5 newtons. Really, really small, especially when you think of space flight, you think of these powerful rockets and, 5 newtons. I mean, that's noticeable. To kind of get the effect, it's, it'd be like holding a cup of water in your hand, because a cup of water would be 8 ounces. 8 ounces would be about a half a pound. And that's about a half a pound. Oh, So just the water, not even counting the glass. So 8 ounces of water, which is smaller than a bottle of water. Oh, that'd be good. Plastic bottle. This plastic bottle doesn't weigh much. So if I took a plastic bottle that only had 8 ounces in it, which again is on the small side, that's what it would be. And if you're pushing a whole spacecraft, depending on what's in the spacecraft, it doesn't seem like it would push it for very much. And it wouldn't. That's what I'm getting at. But it's still possible. The one thing you might have an advantage out in space is not only the big area, but lots of time. And so you might just say, well, I'll just leave it up there for the next 10 years and see where it goes. Type thing. So that's kind of the way this could be worked. Anyways, I think that's the other part of this. What does B say? B says, what is the cell's acceleration? So acceleration, which is force divided by its mass. So the 5.48 newtons divided by this mass of 6,000 kilograms is going to give an incredibly small amount of acceleration. 9.13 times 10 to the negative 4 meters per second squared. So really, 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 really small acceleration. But then it does say what time interval is required for the cell to reach, say, the moon, which is 3.84 times 10 to the, is that an 8? Bigger here. No, I lost it. 10 to the 8th meters away. And then it says ignore gravitational effects, which is a whole nother big picture. All right. So if I were to say something started with 0 speed and I want to know how far it goes, I would go 1/2 AT squared. So we're looking at a distance to the moon of 3.84 times 10 to the 8th meters. We're looking at an acceleration of 9.33 times 10 to the minus 4. And so we can solve this for time. All right, so 3.84 times 10 to the 8th for the distance times 2 divided by my last answer, because that's the acceleration, enter. That'd be time squared. Take the square root of all of that, and we're looking at about a 9.17 times 10 to the 1, 2, 3, 4, 5 seconds. Which then, let's see, if I divide that by 60, that'd be that many minutes. Divide that by 60, it'd be that many hours. Divide that by 24. And actually, 10 days was more than I thought. Oh, yeah, but we're ignoring the effect of gravity from the Earth. So that could be problematic. Huge. But, yeah. Maybe if we're far enough away or halfway or to the point that maybe the effect of Earth's gravity and the moon's gravity maybe are semi-balanced. This is what we're talking about here, 10.6 days. And I better check the number 28. I got 5.5, good. So then they got an acceleration of 9 times 10 to the minus 4. Okay, good. And then they got, 10.6 days. Nice. Nice. All right. Let's see. 28's done. All right. I'm debating here. Jump in. We only got a couple minutes before the break, and I think there's plenty of time to do this in the third session. So why don't we take our break a few minutes early this time instead of a few minutes late? And then we'll come back and do 31, 32, and might even upload. Joshua, I think I will. I'm going to take those few minutes. I'm going to see if I can just send this to my YouTube channel, the first session this morning. I know the second one I can. It's got a process for the next. It usually takes about 30 minutes before I can get a video out of it. This one here, the second one. But the first one should be all done. And I can send that to my YouTube channel. So if you wanted to see number 3, I'll just tell you it's about 12 minutes in. So I'll shoot you an email too. Okay. All right. So call this a stop share and an end.